All right, today we are going to pull together a meta-regression in Excel. In a previous video, I did a meta-analysis using a sums of squares approach to synthesizing the effect sizes. This time, I'm going to make use of some of the matrix algebra functionality in Excel. It's not super elegant, but we could still do matrix algebra, which is important if you want to do a meta-regression. And now, with a classic meta-analysis, it's univariate. You just have the one, you're taking an average across effect sizes, but when you're doing a meta-regression, you're really extending the model to include predictors now. And to do that kind of stuff, the matrix algebra really helps out because parsing out all the equations for that can be difficult, whereas using matrices to describe how things relate to one another really simplifies the estimation of things you want from a meta-regression, which is typically the intercept and slope, all the usual fixings that you want with a regression model, but now you're doing it with effect size data. And so the goals for today, they're going to be straightforward. I'm going to do a fixed effect meta-regression, and then we're going to build on that model to end up with a random effects meta-regression. And much like in the previous meta-analysis video, we're going to use the Simonian layered estimator for the tau squared, what is needed to estimate a random effects model, just because it's the simpler one. You could certainly use more elaborate optimization approaches to estimate the between study variance, but for doing this stuff in Excel, I think it's the easiest way to get it done. Other things I want to talk about before we get started is a little bit about the data set. Let me jump into Excel here. The data set we're going to use for the meta-regression is from Kolditz, al. 1994 JAMA paper looking at the efficacy of a vaccine on tuberculosis. And the reason this is kind of used often for teaching meta-regression is that the efficacy of the vaccine really improves at higher latitudes. And so you get this really interesting geographic relationship where trials performed close to the equator where the vaccine is less effective than trials occurring further away from the equator. And unfortunately, the paper is super unsatisfying in explaining that relationship. They really don't try to provide a causal mechanism for why there is this trend. But nonetheless, it's kind of a neat, repeatable thing we could do with analyses is just to kind of fit that line, fit that slope of how well latitude predicts the effect sizes, which is what we want with our meta-regression. That's conventionally the desired synthesis level outcome of a meta-regression, at least if the predictor is continuous, is all the fixings you typically want with just a regular regression model, which is the intercept and the slope, whether or not those things are non-zero, whether they're significant. Maybe you want to fit a confidence interval around the slope. We could do all that kind of stuff. And typically what is used, and it's not I'm not focusing on this for this video, is the bubble plot or the meta-regression scatter plot. I'm saving that for another video. So really this is like the sister video to plotting a meta-regression results will be in another video. But here, this is essentially what the desired synthesis outcome is a line that is fitted where latitude predicts the effect size, right? This could be anything. It could be age. It could be some other type of continuous predictor. And then here is your study outcomes, your actual effect sizes. We got a line fit, intercept, slope, 95% confidence intervals, and it's clear that there's a negative trend where we're going to try to replicate using matrix algebra, and by using all these nasty looking equations, matrix equations. But if you're familiar with like least squared or generalized least squared or general least squares, they're all using this equation here, the GLS equation. This is fitted for every single regression model. But what you get differently from, say, like a meta-analysis versus a meta-regression is how you code the design matrix. And depending on what kind of design matrix you throw into this equation, the outcomes, the synthesis level outcomes differ. So whether they're an average or whether they're regression coefficients like slope or intercept. And so this is what we're going to do in Excel. We're going to use all these things. These last three things are necessary to estimate the random effects meta-regression. But we're going to start with the fixed effect. And to get to the slope and the intercept, we only need these two. And then we're going to slowly build on the model to get the meta-regressions. Random effects meta-regression. So the slope here is based on a random effect meta-regression. So I'm just going to copy these equations here because I do not fully know them by heart. And what we're going to do first, well, okay, let me just get better seated here because this might take a while to code all this stuff. Okay, so first things first is we're going to create three matrices. And then with these three matrices, we could plug into all these equations here, the GLS equation and V, which is the variance covariance of the regression coefficients. These are useful because we'll be able to estimate confidence intervals and other stuff associated with the regression coefficients. So let's just start with the first matrix we need to code in our meta-regression model, in our fixed effect meta-regression model, is the design matrix, here described with an X. And the design matrix is what you modify to include your predictors in it. And in our case, we have just the one predictor, absolute latitude. So I'm just going to copy these absolute latitude numbers. And then we're going to throw in an additional column before that, full of ones. Let me just change the color here to emphasize that it's a matrix. This is our design matrix. And so this column here will specify in our GLS model to estimate the slope, and this column here is necessary if you want to estimate the intercept. We would drop this column if we only wanted a slope-only model. This would be equivalent to a meta-analysis model. But we're not interested in that. We want a classic regression outcomes, which is an intercept and a slope. Next thing we're going to prep is the effect size matrix. So in the classic formulation of the model, this would be designated as Y. But we call it E here because we're going to include the effect sizes. Excuse me. And these will be our log risk ratios, our effect sizes. And let me change the color of that again. Just to emphasize that we got a matrix here. So we got the X done, the E done. The last one is the W, which is the most complicated one. And the W is the variance covariance matrix of the model. This matrix is pretty cool. This is what you would modify if you wanted to model dependencies amongst effect sizes and do a lot of neat stuff. We're going to keep ours super simple. We're going to assume that each effect size, each risk ratio is independent. And so this model essentially just becomes a big matrix where the main diagonal are the variance components, are the variances, and all off diagonals are zeros. But this is where it kind of gets a little goofy because we start to specify like a true matrix in Excel. And Excel, the way it treats matrices is like a long array. And in order to tell Excel that this is a matrix, I always got to press Control-Shift-Enter. And what that's going to do is it's going to set in Excel that, you know, this block of cells is a matrix, and it won't let me change the elements of those of the matrix unless I press Control-Shift-Enter to specify the matrices. If you do not press the Control-Shift-Enter, all this matrix algebra will not work. Okay, but before doing that, we got to do one trick beforehand because we want to do the random effects model. Random effects, we're going to estimate the tau squared, which is using all these equations here. And basically, you add those to the variances to get the random effects model. And so right now, we're just going to prime the matrices so that we could quickly do that at the end without having to copy and paste all the matrices in the equations again. And so I'm just going to have this little tau squared equals here. Maybe I could put it over here. Which I will set as 0 for now. And then later, when we actually compute that tau squared, we could just plug it in, and everything will get updated, and all the equations will get updated so that we could quickly estimate a random effects model. Okay. So the last bit is to do the W here, which is the weighting, the weighting matrix, and this is going to involve a little bit of acrobatics to properly code that matrix. But once we do it once, we never have to worry about it again. So I don't mind the suffering right now to get it done because it's something we could just forget about once we do it properly. And so what we're going to do now is the weighting matrix will have the same dimensions as the number of variances. And so it's going to be how many variances do I have here? 13. Okay, so the weighting matrix will be a matrix of 13 by 13 dimensions. So let me just do 13 rows and then 13 columns. And then this will be the variance covariance matrix. So you gotta block that whole section, and then you start coding the equation. I'm just going to scoot over here because I'm going to need to grab some of this stuff. All right, so the equation here, the goal is to kind of like transpose the variances on the main diagonal. And so this is going to be a little ugly. We're just going to have a conditional statement here that says if it's the main diagonal, throw in the variance. If it's an off diagonal, put in a 0. So we're going to start with an if statement. We are going to grab all our variances. Okay. If statement, we got to grab all our variances. If all these variances equal the transpose of all these variances, and that's just like a way to crawl the main diagonal of a matrix. If that's true, then throw in the variances on a diagonal And if it's an off diagonal, throw in a 0. Okay, so I'm just going to copy this. And I need to grab my block again, 13 by 13 matrix size. I got 12, there we go, 13 by 13. I'm going to paste this in here. Now, when I press Control-Shift-Enter, it's going to fill in all the elements in the matrix, if I did it right. There we go. So here we have our 13 by 13 matrix. I'm just going to change the color to this again to emphasize that it's a matrix. And we got all our variances on the main diagonal, and we got zeros in all off diagonals. That's the classic structure of the variance-covariance matrix. We have variances, but we got no covariances because we're not modeling the dependencies amongst effect sizes. Now I'm going to modify this equation again because I want to set it up so that we could quickly do the random effects model later on. And so I'm going to add the tau squared, which right now is specified as 0. As 0 tau squared means you're still kind of modeling a fixed effect model. And so now I'm going to do the Control-Shift-Enter again. Everything stays the same, but now we're set up so that once we have the tau squared, once we estimated that, then that whole matrix gets updated for the random effects model. With these three matrices, now we can start actually doing our meta-regression. And I'm just going to stick these right here. And the first goal will be to estimate the variance covariance of those regression coefficients, just because we use that part again to estimate the coefficients. So first we're going to do V, estimate V, then we're going to estimate beta here, which is the meta-regression coefficients. All right, so here it gets a little tricky because we need to know the dimensions of the V matrix. And because we only include one predictor in a model, right, our model has an intercept and the absolute latitude, our variance covariance matrix will be a 2 by 2 matrix, right? Just because we have 2 columns in our design matrix. So I'm just going to block out a 2 by 2 matrix here, and then I'm going to throw in this equation. And Excel has some canned matrix functionalities. We're going to use the inverse of a matrix, and we're going to use the transpose of a matrix, which is described here as a T. And then finally, we're going to do a matrix multiplication. And Excel only does pairwise matrix multiplication. So we're going to be using that function over and over again to multiply multiple pairs of elements within the equation. I mean, that's what you got to do to get this done. And so our first chunk here of the variance covariance equation for the regression coefficients is an inverse of the matrix. For that is just M inverse. And this is the -1 part, so we're like inverting the entire equation here. Next is to do the first pairwise multiplication, which is the design matrix, the transpose of the design matrix times the inverse of the weighting matrix, W. And the way you do the pairwise multiplication is M mult. That's the name of the equation. And it has 2 elements in the equation, whatever you're multiplying on the left and then whatever you're multiplying on the right. So first thing we have on the left is the transpose of the design matrix, X. And then we have the inverse of the weighting matrix on the right. And let me just close off that equation. All right, so one last element to multiply is we need to multiply the design matrix again, and that will throw in another alt here. And then that belongs to the design matrix right here. All right, so from that I need to do Control-Shift-Enter again, and that should fill up the elements of all the variance, covariance of our regression equation. Okay, I messed up somehow. So we got one multi, we got our transpose, yes. Okay, Control-Shift-Enter. And that is our variances for the intercept, the variance for the regression coefficient, and then the covariances between the two. So then we're going to, let me just change the color of this because this is another matrix. Okay, so the next thing we want to estimate is the regression coefficients. And the dimensions of that matrix will be the number of columns in our design matrix. So we have 2 columns, so that's going to be a simple vector with 2 rows. And I am going to, where should I stick that here? I'll stick it right here. Change the font and the color for this just to emphasize. That we're estimating the regression coefficients. And again, this is going to just be a simple matrix with 1 column and 2 rows. I'll just change the color for that right now. All right, so I want to select those 2 cells in that matrix and then put in this equation. Right here, we already did this chunk. This is part of our variance covariance. But now we need to multiply this other bit right here from the general least squared equation. So mult is our function for multiplying 2 matrices. First matrix in that is the V. And the second is this stuff right here, right? So we need to build this part of the equation in this element here. And so I'm going to start by multiplying the design matrix with the inverse weights again. And I need to take the transpose of the design matrix, multiply that by inverse of the weights. All right. Then we need to multiply that by all the effect sizes. So we need to throw in another mult. I don't know how else to call that function. mult, matrix multiplication. And then we're going to throw in our effect size matrix here. And then just close off. So to fill in that matrix with the regression coefficients, I need to press Control-Shift-Enter. Otherwise, nothing's going to work. There we go. So we got our intercept. Let me zoom in on this. We got our intercept. And we got our slope, which is negative, which I kind of knew beforehand in the relationship of using the bubble plot. All right, so our model is making sense. Now, let's just quickly write some text way to report these meta-regression, fixed effect meta-regression results, right? That's what this is right here. We got the slope and the intercept. It doesn't make sense right now because it's in matrix form. And so let's quickly modify these so that it's what you would report in a manuscript or a paper, the regression coefficients. And so this is called the intercept. This is called a slope. Could zoom in some more. We're going to round these numbers off. Say round it to 2 decimal places. Now, what kind of things do you want? Well, let's do it 3 because the slope is small. So what do you want paired with these regression coefficients? You want their standard deviations. You want 95% confidence intervals. That's super easy to calculate because we have our variance-covariance matrix of the regression coefficients. So let's do standard deviation, 95% confidence interval for the lower bound, do the upper 95% confidence interval. And then on top of that, we're going to estimate the significance of each of these regression coefficients. So is the intercept non-zero? Is the slope non-zero? The way we do that, we use a z-test, which is something that's commonly reported in all sorts of meta-regression stats. Basically, what we're testing is whether or not that coefficient is non-zero, whether it's significant. And so we're going to calculate the z-test for that, and then the p-value of that z-test. Okay, so let's start with the standard deviation. We got the variances already. Whoop. We got the variances already, and so standard deviation is the square root of the variance. And then because we have a matrix, we got to shift over. So the main diagonals of the variance-covariance matrix is the variances for the intercept, variance for the regression coefficient. We don't need to worry about the covariances right now. We only need to worry about the covariances once we start plotting the confidence intervals around the regression line fit, right, for the bubble plot, which is not part of this video. I'm going to do that once we actually do the plotting video. 95% confidence intervals, you take the intercept, you subtract 1.96, which is the standard normal deviate, multiplied by the standard deviation. And then there you have the lower confidence intervals for the intercept and the slope. And then do the same thing for the upper confidence intervals. But this time you add. All right, so based on these confidence intervals, the intercept is non-zero, positive, and the slope is non-zero, negative. Okay, so these would be considered both significant. A z-test, we could calculate that to complement the significance. You know, I prefer the confidence intervals, but sometimes you're asked to provide a p-value for whether or not something is non-zero, and a z-test offers that opportunity. Z-test is the regression coefficient divided by the standard deviation. I should technically be using the non-rounded version for all this stuff. So let me just quickly fix these equations here to improve the precision. I don't know why I used the rounded version. All right, finally. Improve the precision of the z-test by not including the rounded version of our regression coefficients. There we go. All right, now the p-value of these things is the z-test is tested against a cumulative normal distribution, assuming that the mean is 0 and the standard deviation is 1. In Excel, we got all those functions to do that, and so let's quickly parameterize it. One, we want it two-tailed, and so we want to multiply it by 2. 2 times 1 minus norms s dist. That used to be called norm dist in old Excel, but now it's called norm s dist. We want the absolute value of our z. And then we want to say that, yes, we want the cumulative distribution function, so we write true. And then we close it all off. There's our p-value, which is super small. And so in terms of like reporting it in a paper, you would say it's less than 0.001. I'm not going to do that here, but I think you guys get the idea. This is what you would report in a paper. You report the intercept, report the 95% confidence intervals of the intercept and the slope. Alternatively, you report the intercept and the slope and the z-tests. All right, I think this is looking good. So this is what we'll call our fixed effect meta-regression. Right, we got our intercept and our slope, and everything is done. Now we need to follow through and build on this to estimate the random effects model, which is the slightly ugly part because the equations are, whew, they are ugly. Let me just throw these equations right here. All right, so we did our fixed effect model. Excuse me. Now the goal is to estimate the residual sum of the squares, which is also known as like a homogeneity test. You know, Metaphor in R likes to call this the test for residual heterogeneity. Not crucial for what we want, but we need it to estimate the between study variance because we're using the Dersimonian layered estimator, which plugs that in to estimate the tau squared. And so before we get to estimating the residual sums of squared here, the QE or the Q error, the residual homogeneity, residual heterogeneity of the model, we need to calculate P. P could be just called anything. I'm just trying to simplify the matrix algebra here because it's a ton. And I don't think Excel could do all these levels of matrix algebra. So I just cut it up into 2 chunks so that I avoid issues for you guys. So the first thing we're going to do is estimate P. I'm going to bring it over here because there's no room for that on my sheet. All right, so what is the dimensions of P? You need to know the dimensions before you could do Excel matrix algebra, right? And so let's investigate the equation here for a second. It's using W, which is our weighting matrix, and it's subtracting with a whole bunch of mumbo jumbo. And so these matrices have to be the same dimensions in order for the subtraction to occur. That's just like matrix algebra. And so all I need to know is the dimensions of W, and I know the dimensions of P. Dimensions of W is 13 by 13. We already specified it over here. And so what I need to do is now block off a 13 by 13 section of the spreadsheet to allow for the calculation of P. I'm going to change the color of this to again emphasize that it is a matrix. All right, now we need to do some more matrix algebra in this thing. First things first, we need to specify the inverse of the weighting matrix. Which is our W. And then we want to subtract all this stuff. Now I'm going to build this chunk of the equation from the middle outward, just because I gotta tie together a bunch of pairwise multiplication functions to calculate this. And matrix algebra does follow a certain order. Things that are not compatible shapes, you can't do the multiplications with. And so feel free to rewatch this section over and over again. I'll have the equation up here highlighted so that you can see what I'm doing. But first things first, I'm going to multiply the design matrix by V. We already calculated V. V is the variance covariance matrix of the regression coefficients. All right, so first we want our design matrix times our regression coefficient variance covariance matrix. Okay, we did this chunk. Now we want to multiply the transpose of the design matrix. Okay, so we did this little sandwichy part of the equation. Now we need to build up with the inverse weights, which bracket this little sandwich part. And so we're going to do the first part here, which is the inverse weights times this stuff that we already got going. And then one last mmult to multiply this little bit of the equation. I mean, this really looks like nonsense in Excel. And I need to take the inverse of that matrix. Okay, let's see if I got this right. Normally I never get this equation right at all, so I'm just going to try it. Control, Shift, Enter. If it works, that'll be fantastic. If it doesn't, well, I'll need to refactor this equation. Oh, great. Control, Shift, Enter. Ah! All right. We got something going on here. Yeah, that's it. I did it in one shot. Okay. That's a win for me. I haven't done that yet. All right, so here we have our P matrix. You know, it's just a nonsense. But this is just a shortcut to be able to calculate the residual squared error here. And so let's just finish off by estimating the QE. And then we'll almost be done. All right, so QE is just one value. Okay, so it's a matrix of like 1 by 1 dimensions. And so now I'm just going to throw in our equation, because what we're doing is just multiplying the transpose of our effect sizes times the P, which we just did, times E again. So that's pretty easy to pull together. Transpose our effect sizes times P. We don't need to do anything special to P. And then finally we do another mult, because we want to multiply that section with our effect size vector again. All right, so to fill in that cell, I need to do the Control-Shift-Enter. And there we go. We got our QE, which equals 30.7. Okay, so that's our residual squared error of our model, which we'll use to plug into our Dersimonian layered estimator for the tau squared. For fun, we could calculate the p-value of this QE. It has a chi-square distribution. So 1 minus chi dist. Got 30. We need the degrees of freedom, which is the number of effect sizes minus 2. Minus 2 because we have two chunks in our regression model, the intercept and the slope. In our case, we have 13 effect sizes, minus 2. And then finally, we want to specify the cumulative distribution function to estimate the p. There we go. There's our p-value. It's significant, right? So this is good. That's the whole reason we're doing our random effects model, is because there must be a ton of between study variance. And so now we're going to include that between study variance in our model, hence the random effects meta-analysis. But first we need to calculate our tau squared. And that equation is fairly straightforward. It's right here. We have a conditional to this. This is part of the Dersimonian layered estimator. Sometimes you get a negative value, and so we don't want you can't have a negative variance. And so if it ever ends up being negative, we just assume it's 0. Otherwise, ignore it. All right, so max 0. And then we just, oh, freak, I forgot to do the trace of the P. Ooh, trace of the P is ugly. So a trace is essentially summing the main diagonal of a matrix. Excel does not have a trace function. And so we need to find the sum of the main diagonals on this here. And so I'm just going to fit that in this bit over here. It is not super straightforward to figure out. What we need to do is just tell an index to crawl on the main diagonal. So I'm going to create 2 rows here with just like numbers going up to 13. Those are our indices to specify the main diagonal. And then now we want to do the index, right? So one way to tell Excel to pick certain elements within a block, you use the index function. So we got our matrix here, and then we just tell it, hey, oops. Hey, just look at elements 1 and 2, and then pull those numbers out for us. I gotta specify that the matrix never changes. Excel does this. I don't know why it does this. It tries to be smart, but it's not smart. Here we go. So we want the sum of the main diagonal here, which is the trace, and the last real thing we need to estimate for our model. Whew, this is the longest video I've had to make. All right, let's quickly finish off this equation here. This one right here, and then we're done. Well, not quite done. Almost done. Thanks for sticking around this long. All right, max. And then finally, we want the trace of the diagonals of P that we just figured out. And then we want our QE, which we just calculated, minus the degrees of freedom in our model, which is, we got 13 effect sizes minus 2 coefficients. And there we go. Now let me just zoom in here. We got our tau squared for our model. With the tau squared, now we can estimate the random effects regression coefficients. So I'm just going to copy this here and paste it as values. All right, so now I'm just going to take this number here and then throw it in this cell that we pre-specified that helps adjust all these equations so we don't have to do anything crazy. And we're going to call this one the random effects. Random effects meta-regression. All right, so now I just need to take this value here and then put it in my value. I think I'll just write the number, 0.063301. And then there we go. We have our random effects, regression coefficients, and we have our fixed effect regression coefficients. We did it. I mean, it was ugly to get this done, but we got it all together. This is the stuff you would report. The results are different between the models, right? So the intercept was significant in the fixed effect model, but it's not significant in a random effect model. However, the slope, it remains negative in a random effects model. And so that's good. It means like, okay, this is a meaningful predictor in our analysis. And I feel like I need a break because that was a lot of work. All right, well, we did it. I mean, I don't know what else to say other than you could do matrix algebra. You could use the GLS equation in Excel. You could estimate the fixed effect and then build on it to get the random effects model. This is like essentially what all the CAN software does for a meta-regression. On your end, though, now you have it more explicit if you want to throw in covariances and things like that in your model to model some dependencies. You could do it all. It's all specified right there. All right, so I'll end it with that. There's going to be another video with this that'll help you plot the bubble plot here. Okay, so that's making use of the random effects meta-regression coefficients to plot that. And so thanks for watching. If you got other suggestions for videos, that'd be great to hear from you guys. And I don't know what else to say. I need a break. Take it easy.